So I'd like to welcome you all to the panel on the smart grid, looking beyond smart meters. So when the director of ARPA-E, Arun Majumdar, asked me to moderate this panel, I asked him, what exactly is your goal? What are you hoping to be able to discuss? And his goal was really to be able to show people that there's a little bit more going on to smart grid than just thinking about smart meters. That he wanted to invite panelists that would help paint a technology vision for what the smart grid might be. So my name is Rajeev. I'm a program director here at ARPA-E. I run the grids program as well as the power electronics program. So we've already got some investment at ARPA-E into things that you might call the smart grid. Now, one of the things I wanted to start off, just basically giving a little bit of context with some of the discussions we'll have today, is really what the smart grid might actually mean. I think almost everyone I talk to has a different definition of what makes the grid smart. One of the things that we should consider, and maybe this is a slightly odd perspective on the topic, is whether the grid is smart today with the large-scale deployment of smart meters really kind of depends a lot in terms of what you think intelligence really means and what your definition of it, what it means to be smart. So we think of a smart meter today. Right now, a smart meter is really a sensor. It's a network sensor that has some ability to communicate information back to you. Now, if a sensor was really all it took to be smart, we might measure intelligence by the size of someone's ears, right? We don't think that's a really unconventional definition of smart and intelligent. If we want to think about a more conventional way of looking at how smart or how intelligent something is, we tend to have different measures. A more conventional measure of intelligence might be how well you process or analyze information. And by that measure, the grid is not really that smart today, even with the deployment of smart meters. Another measure of smart or intelligence might be your ability to react to that information, react to the sensor information. And what we'll hear about today is really that the grid at this point, the grid today is really not at the point where it's able to react. So I think hopefully you'll see some themes that come out in terms of where the grid is today, what smart grid might mean, how the smart meters today represent only a starting point and really not anywhere near an end point for what we'd like to be. So with that, I want to introduce our panelists. The format for today's panel discussion is going to be a quick introduction to each of the panelists. They're going to say a few words, give you a little bit of background in terms of their organization, a little bit of the vision that they see for smart grid technologies. We're going to open it up to questions from the panel and then basically end with some closing remarks. So you'll get a chance after the comments are basically been made and we've started the panel discussion to come up to the microphones and ask questions to our panelists. So with that, let me introduce the panelists to you. We've got Paul DeMartini. Paul right now is at Newport Consulting. He comes to Newport Consulting after having been Chief Technology Officer at Cisco Smart Grid. Before Cisco, he was Senior Vice President at Southern California Edison and oversaw a lot of the deployment of smart meters and really developed strategy for what smart grid might look like. So we're happy to have Paul here joining us today. Sitting to Paul's left is Arshad Mansoor. Arshad is at EPRI. For those of you who are not familiar with EPRI, it's a nonprofit research institute that supports the global utility base. I think about 90% of all the electricity generated and distributed in the United States passes through the EPRI membership. Arshad is a senior vice president at EPRI, and he basically enters that position after having spent several years being vice president of transmission and distribution at EPRI. To Arshad's left is Andy Ott. Andy is Senior Vice President of Markets at PJM Interconnection. And for those of you who know that PJM basically runs the largest electricity market in the United States. We used to be able to say the largest electricity market in the world, but I think China's a little bit larger now in terms of the size of the grid that they operate. And so we're happy to have Andy joining us today. And last but not least is Deepak Divan. Deepak is President and CTO of a new company called Varentec. Deepak spent many years at Georgia Tech as an academic, but while at Georgia Tech also being a serial entrepreneur. And also, I believe he's former past president of the IEEE Power Electronics Society. And so really we've got four very different perspectives that hopefully will be available for you guys to tap into in terms of envisioning what the smart grid might look like beyond just the deployment of smart meters. And so with that, let me turn it over to Paul for his initial comments.
Thank you. Well, it's a great opportunity to have a discussion this afternoon talking about where we where the smart grid's heading, where we're going with the electric system in the United States and frankly around the world. So maybe just a couple of context-setting slides. Oh, sorry. So as was just touched on, I see 4 transformational trends that are underway. We've talked a little bit about this already today, but I think it's important to put it into context because, you know, maybe there was a suggestion in some of the earlier conversation that change isn't happening all that quickly, and I would suggest that it is, in fact, happening rather quickly, and on all 4 dimensions that I've got listed here. As was touched on, sensing and response, certainly smart metering is a component of it, but much more than that. Synchrophaser technology that's being applied in terms of looking at the health and strength of the electric system, particularly at transmission, but also looking at applications at distribution, and certainly other sensor technology that's coming on to bear to look at asset optimization as we look to manage the electric system more efficiently. But beyond that, as we look at the demand side, both in the industrial, commercial, and residential level, how sensing technology and sort of these lower cost sensing and communication technologies can enable us to integrate responsive demand and understanding the state information of energy consumption and integrating that into system operations as well as into markets is something that's clearly well underway. I don't need to say much about clean generation. I think there's been a lot of discussion on that. I would touch on the concept that Metcalf talked about some years ago called the Internet, and we are clearly seeing the evolution of more connected devices on the electric systems, both the United States but also worldwide. And that is starting to have us look at what is possible by the end of the decade, and it's quite clearly heading in a direction in which many more devices are going to be integrated in both to the markets but also into the control systems to manage the system more effectively. And then prosumerization. This is the concept where not only are the end users today consuming but also producing. And we're well underway in terms of the adoption of on-site generation in many forms, but certainly notable in terms of solar PV and the like, in terms of how that becomes a critical resource, not just in terms of offsetting consumption on the customer side, but also potentially contributing into the markets and into to grid operations at the distribution level and potentially farther upstream as we reach scale. These are all clearly tracks that are underway, and the progress that's been made over the last 15 years has certainly outstripped some of the things that were discussed earlier today. There's a tremendous amount of activity, much of which many of you are involved in. And this isn't just because people are thinking it's going to happen. The public policy is driving this. When we look at both the renewable policy, although we may not have a U.S. federal standard, certainly you look at the number of states representing the a large amount of the population in the United States, the public policy is already there to drive this. Certainly solar PV in terms of the pricing, which I'll touch on in a second, has certainly accelerated the adoption in many places. And of course energy efficiency policy, long-standing, but certainly the latest initiatives have started to push this effort towards the zero net energy, zero carbon objectives. Of course, solar PV reaching retail parity. There's a lot of discussion classically talking about reaching wholesale parity, but sometimes that overlooks the fact that at the end customer, if you can reach retail parity, you're going to get adoption, and that's exactly what we're seeing in a number of places around the country. And in fact, you have a CEO of one of the leading energy companies, David Crane, here recently, and in November, but also more recently, just a week or so ago, reiterating that in their belief, they see solar power reaching retail parity in at least 20 states within just a couple of years. This is significant transformation underway and significant impact on how the distribution and transmission systems will be operated. We're not going back. This is moving forward, and it's moving at a pace that's accelerating. So what are the implications for the work that we're all doing on smart grids and related technologies? Well, I would suggest that there's this convergence that's underway. And to paraphrase sort of an IT analogy, For the better part of the last century, we've sort of operated the electric system in a series of abstract layers. So the layer at the premise, the layer at the distribution, the layer at transmission, a layer at markets, and then as we've now started to see the phenomenon of how social networks can interplay, we now have these multi-layers. And these multi-layers can no longer be abstracted. When we start to have significant penetration of distributed resources, we need to think about the implication on distribution, but also potentially the interface with transmission. And this is already part of the dialogue that's happening in Europe, for example, where they already have fairly significant levels of penetration of distributed solar and wind, actually, on distribution level, and how that interfaces with transmission. And, of course, the interplay between markets and the grid, whether it's transmission or distribution, and the more recent phenomenon, if you will, over the last decade of social networks and how that starts to integrate into this. As was touched on earlier today, this is certainly a complex system. In fact, one of the most complex systems that exists around the world when we talk about the electric system and how it's operated. But there's clearly an opportunity here to think about how we might evolve this, not unlike how we've evolved other networks, how we've evolved other operating paradigms. Clearly, there's a unique characteristic about electricity related to the fundamental support of people's lives that we don't lose sight of. But that doesn't mean that progress can't be made, and progress can be made rather quickly, actually, as I touched on. And so there are a couple of areas that we've discussed here. And from a research standpoint, I'm encouraged by the number of academic and national labs and entrepreneurs that are putting a lot of time and effort into addressing these questions about how do we start to integrate not only millions of distributed energy resources, whether they be supply side, whether it's on-site solar or other distributed generation, or more responsive demand, to the point at which we may be looking at individual devices in the tens of millions by the end of the decade into various particular systems, and the transactions that go in line with that. This is an area ripe for entrepreneurship. It's an area ripe for research, and clearly we're on a good path, and ARPA-E is certainly helping to spur that along. Thank you.
Thanks, Paul. Thank you, Paul. So next I'd like to invite Arshad to make a few opening comments.
Thank you, Rajeev. Good afternoon. Didn't hear any response. Let me try it again. That's right. Good afternoon. Clearly, none of our panelists, very esteemed panelists, none of our name is Bill Gates, though, so I can see from the side of the room. It is an honor and pleasure to share with you some of our thoughts on what the future of smart grid could be. But as I was thinking of future of smart grid, I remembered what Secretary Chu mentioned, a quote from the famous philosopher Yogi Berra. Predicting the future is an effort in futility. That's my paraphrase. So instead of predicting the future grid, why don't we take some time and see how we can shape the future grid? And if you look at shaping the future of electricity, those of you know EPRI, Electric Power Research Institute, that is our core mission. We have more than 550 engineers and scientists. But we work with national labs, we work with universities, we work with vendors, and most importantly, we work with more than 400 electric utilities throughout the world with a singular purpose. And the purpose is how to make electricity reliable, affordable, and environmentally responsible. Now, for a scientist, for a technologist, the challenge is much easier if we have to maximize any one of those three things. I think if the goal is how to make the most reliable electricity, we can do that. If the goal is how to make the most affordable electricity, we can make it happen. If the goal is to make the electricity most environmentally responsible, we can do that too. But when you have to balance all three, the challenge is a daunting challenge. And the challenge over the next 10, 15, 20 years, people who are involved in the industry will say for the last 120 years, the changes that we have seen in the industry, we will see more in the next 10 years. And the reason is what you heard this morning. Our resource portfolio is going to be changing. The mix of coal, gas, solar, nuclear, wind, that will dramatically change. And as that changes, the grid has to change as well. The grid has to make sure that it is the enabling function that allows us to bring all the resources as the resources become cost competitive. So with that as the kind of setting the stage on the future of smart grid beyond smart meters, let me just focus on one key area that we see we need to redouble our efforts. There are many technologies that you can see at the showcase, and there are technologies that you heard this morning, and all of those are important technologies. But as we look at evolution of smart grid, anybody want to venture out how many smart meters we have installed in US? A number? 10. Close, 30 million. So 30 million smart meters, and that's not just smart grid. We are installing phasor measurement units. We are overlaying IT as part of the grid. It's not just happening in US, it's happening overseas too. Every utility is moving at different speed. You heard Bill Gates this morning talking about public service commissions, and investment in the grid has to be approved by the Public Service Commission. So different utilities are progressing in different speeds. But one thing that is clear, the one thing that is clear is we will be drowning with data. And there was if you look at in UK, once they deploy all the smart meters, and I'm just using smart meter as an example, think about this. Think about, go to Southern California Edison, Paul's previous utility, 4 million, 5 million customers, all the houses. Think about there is a sensor now in all 5 million houses that is sending you some information, maybe 15 minutes, 30 minutes. Multiply that by 5 million, multiply it by 30 million. Look at the amount of data that you're collecting or you will be collecting. Think about the phasor measurement units that we are installing. Think about all the electromechanical relays. Those of you in the power world, all of you know the electromechanical relays. We are replacing all of them with digital relays at different speed of transition. So we will be swamped by data. There is a tremendous opportunity to show to the customers how the data can make us better. If our goal is affordability, reliability, and environmental responsibility, there is a tremendous opportunity as we are collecting the data to look at how the data can allow the grid to be smarter. And there are many, many, many ways you can do that. We haven't even touched the surface. We haven't even looked at the many possible ways that the data can be used for a smarter grid. I'm going to offer you a slide. I know it's a busy slide. One of the cardinal rules is don't make a slide busy, but this is made busy intentionally. Just look at those words, phrases. Just look at those words, phrases, see what in your mind you see, what do you see out of those things? They all have a central theme. I'm going to go and look at somewhere there you will see, hopefully there is a geospatial mining. If you look at the top, what is geospatial mining? If you don't know, you know Google Maps. So Google Maps is an example of geospatial mining. And why do we care about that? So just think of a scenario. You heard Senator Lamar Alexander this morning talking about electric vehicles. He was absolutely correct in saying that we have enough generation capacity in US. During nighttime you can go to sleep and you can charge your electric vehicles. Yes, you can do that. But the transformer that's serving the 5 houses is already 120% loaded. So while you're sleeping and you're charging all 5 vehicles that are in the 5 houses, you need to make sure you have good, actionable information coming out from all the elements in the grid that is distributed across hundreds of thousands of miles. And geospatial mining allows you to do that. If you have a smart sensor in everybody's house, and if that data is integrated with the utility GIS, Geographical Information System, you should be able to correlate that, and at any point of time, you would know how much loading you have on your system. That's a great advantage of using the data from metering. Just take one step further. In last couple of months, how many storm events have you seen? In Northeast, you had the winter storm. You had a big, huge wind event over on the West Coast. You have millions of customers down. It still sometimes takes 1 week, 2 weeks, even with all the heroic effort of the linemen and the crews. You may be 3 weeks out of power. So take this thing one step further on data mining. If you have data coming from your system, and if you can overlay that data with your geographical data system, if you can overlay that with your outage management system, if you can overlay that with your work management system that dispatches crew, you may be able to much more efficiently dispatch. Maybe within 3-4 hours of the storm, you will be able to do a damage assessment, you would be able to dispatch the crew, and you may be able to shorten the restoration time to 20–30%. So one of the challenges we have in smart grid is connecting with the consumer. What is in it for them besides I am able to read the meter in an automated way? So if you can reduce the restoration time by 30–40%, and in the electric utility industry, people are seeing that. And when I was talking with Paul, and Paul was saying, if you look at a distribution system, the people who are operating the distribution system most likely don't have the visibility of the data that's coming from smart meters or the relays or other sensors that are in the system. There are absolutely valuable information on those billions of events that's happening. So one of the key focus, in addition to all the technology development, that as we go beyond smart meter, we need to make sure that we are using the smart metering data much more effectively. We absolutely will do other things. We absolutely will deploy technologies that make sense in terms of affordability, reliability, and environmental responsibility. But if you have already invested this much money in putting 30 million meters, and you will be putting 50 million in the next 5 years, why not do everything that we can to make more use of the data to make the grid smarter? Let me end up with, shaping the future requires all of us to take an action, not just talk about it. So if you look at how do we shape the future in terms of ensuring that the data that we will be collecting in this widely geographical network grid, unlike any other system, is actually a very complicated thing. You have every node connected with every node. The wall outlet right there is somehow electrically connected with the wall outlet out in Florida. So when you have that vast of a system and you're collecting all the data, there has to be a way that we can harness the data. We see two ways how we can shape the future. One is long-term. And actually the long-term work has already started and progressing very, very well. Many of you are aware of the National Institute of Standards and Technology, the NIST-led effort on Smart Grid Interoperability Panel. Because once you take data from all these different systems and you overlay with your geographical information system, you overlay with your outage management system, unless you have standards for those data and standards at all layers, you will not be able to do effective end-to-end integration. So in the world of standards, work has already started. Not started, some of the work is actually well underway. And NIST is leading the effort. IEEE, IEC, other standards organizations are feverishly working on it. So the long-term foundation, the work is actually progressing well. What we now need to do is look at the more short-term, near-term. Standards take time. Changing of an OMS system from today's OMS system, the next OMS system will take a decade. But we already are collecting data now. We already have an OMS system. We already have a system. So why don't we bring the experts together, the experts in fields of data mining that are not power system experts, the experts in power systems, get the power system model, and then look for all incremental opportunities. This vast amount of data will allow us to make a smarter grid. And that's the effort that we have undertaken working with utilities. But it's an effort that will require a lot more than EPRI or the utilities. It will require all the brilliant mind that has looked at data mining, artificial intelligence, pattern recognition, all those things in other fields outside electric utilities. And by bringing them together and working in the short term, I think we can continue to show the value of a smarter grid as we are working on the standards and other areas that will allow us to do more effective data integration. Thank you.
Thanks. Thanks, Arshad. So next we'll call up Andy Ott from PJM.
Thank you. Good afternoon. And again, I'm honored also to be invited to be here. Thank you for the invitation to speak today. PJM essentially is the power grid operator, the air traffic controller, if you will, for coordinating the asset utilization in the area that we serve. What I'd like to talk about from our perspective, again, is if you think about the change in the industry, this industry, you may have missed it, but we have evolved considerably as an industry, I think, in the past, say, 20 years. We'll talk today about many of those evolutions. One we're right in the midst of is essentially an evolution of supply and demand. If you actually look at what we're encountering as an industry right now, the supply mix, the traditional resource, the thermal plants, they had traditionally been the supplier of flexibility. Customer was king. When I started in the industry back in the 80s, the customer got whatever it needed. It was our job, essentially, to create sufficient resources to make sure the customer served no matter what. Today, I think you see a lot more pressure on supply, whether it be environmental restrictions, whether it be cost, whatever, delivery issues. They have less and less capability to be flexible and to provide those services that the grid needs to be controlled. You get renewable resource penetration. They're intermittent. They really aren't built or don't provide such service. So what you find is that effectively on the supply side, you have less control, you have less flexibility, you have less ability for grid services to be provided. If you think about the demand side, you've seen some, at least pilot projects, if not more than that, where technology has enabled demand flexibility. And in fact, in the PJM market, we've actually rewarded such demand for being flexible by providing them a revenue stream and actually allowing them, whether it be an alternative resource or a demand-based resource. We've had significant success with them creating a business model to provide grid services. So it's almost an inversion. You're seeing an inversion where prior to the state we're in, the supply side provided all flexibility, and I think we're seeing it starting to turn. It hasn't yet flipped 180 degrees, but that evolution is on the horizon. As far as the markets go, part of what PJM does again is provide the price, not only control signals, but also price signals, investment signals, if you will, to allow technologies to essentially maximize value or bring back value to those who bring them to the market. So part of what markets do, again, and the PJM market in particular, is to provide both price signals in the short term and hopefully in the long term. What we're seeing as far as markets, we've had a tremendous evolution in the wholesale market in PJM in the past 10 years, but I see it growing more. I think we're going to have more focus on some of the real-time grid services. You're probably going to see more development in those areas. Also forward demand response type or forward alternative resource price signals. And I'm talking forward in the sense of multi-hour prices where we're actually put out prices that are probably somewhat guaranteed so the demand resources can actually take them and respond to them, because a real-time price signal is not something that generally speaking you're going to get a tremendous amount of volume of response on that basis. The other is forward price signals. We're talking multi-month, multi-year type investment-based signals, whether those be on-peak, off-peak swaps, whether they be forward contracts for grid services. You see that type of thing evolving. I think when I talked about what has the market done, this industry has evolved from, I started here in the industry back in the 80s, I'm dating myself, but it's tremendous amount of change in the time that I've worked in this industry. One of the changes we've seen at PJM, this is actually in place, is how we actually control the power grid from a central dispatch perspective. We had gone from a relatively simple central dispatch program that was based on security constrained optimization to something that now, instead of just looking at a single point or a series of individual points in time over the next hour or two, we actually now have a time-coupled optimization engine where you have multiple mixed integer programming-based optimization engines actually looking out in time. They're coupled in time, so you actually get a dispatch, what we call dispatch trajectory. So you're actually projecting over time how the resource should respond, which is much more sophisticated control. It gives us a lot of visibility into the state of the grid and the state of what we need from resources. We can then provide that same information back to resources to again maximize their value, allow them to maximize their value back to the grid. So that type of innovation we see that probably projecting further into the future. Today we have accurate signals out about 120 minutes. I would suggest that as we look forward in the future, you'll probably see that go out a little bit further in order to allow demand innovation. Thought it might be helpful also to talk about some of the things we're seeing as far as innovations that are making their way into the market. One is, again, storage provides tremendous value in frequency regulation. One aspect of this particular battery installation provides frequency control, so it's a very high-speed response to our control instructions. In fact, they respond faster than we actually need them to as far as their capability. We're generally looking on the frequency regulation for 4-second type response. These types of devices can respond even faster than that. So that type of service we actually have a market for, and we pay an hourly price. And in fact, that's getting more sophisticated. We're actually moving to a pay-for-performance-based market where the entities who perform better would actually get more revenue, which hopefully will incent even more investment. This, again, is the different types of technology pilots we have going. Some of these are demand-based in the sense of whether they're aggregating various smaller demand customers together and offering them into the market as a resource, or whether it's a alternative type resource based on some type of storage technology or other technology. So what we're seeing is a fair amount of this stuff occurring. People are experimenting. They're using the markets to determine can they actually make this work commercially. And we're seeing a fair amount of interest in this space. I think as we look at what's beyond smart grid, again, I think we've actually seen a fair amount of innovation already. A lot of the pilot projects I talked about are probably moving beyond what I would call pilots and actually becoming commercial. Obviously, we need to worry about cybersecurity, or we're going to have issues as we move forward. I think as we look at the way PJM at least has deployed the control systems, the sophistication with which we operate the grid has changed tremendously, and education of both the customers and the workforce has been a tremendous challenge. But also getting customers themselves to understand how their contribution to the market would provide value back to them. This integration of the market signal with essentially a control signal back to customers in the way of prices. That's probably the area where I think we've seen the least amount of innovation in the industry, is the business model for the way the industry works on the wholesale side and on the grid operation side on a transmission has been a fairly significant and constant change over the past 20 years. The actual delivery of that to customers, though, and the customer's bill is the same. It hasn't changed. We're still billing customers based on as if the same electrons cost the same at 2 a.m. as they do at the peak time of 4 p.m. So that's going to need to change. But I would comment that I think we already have the technology to do what we need to do as far as move to an intelligent grid operation and to leverage all of the innovations. I think really it's more of a coordination effort. It's coordination both in prices to customers, it's coordination in investment signals in a wholesale market type context, and it's basically coordination of all the various technologies to actually work in the most efficient manner. And thank you for your time. I look forward to your questions.
Thank you, Andy. Last, I'd like to invite Deepak Divan to come up to the podium.
First, I'd like to thank Rajeev and ARPA-E for the chance to come here and share some of our thoughts on this topic. Also, I'm in a very privileged panel out here, and I think you've heard some very interesting perspectives. I'm going to try to present something maybe slightly different. I mean, it's been our belief that utilities are beginning to face a new paradigm as far as grid operations are concerned, and I want to kind of talk to that just a little bit if I can. I mean, one of the things I'd like to kind of say is that utilities are extremely smart, and their operations are extremely smart. I mean, they have been doing things for over 100 years with a system that demanded on-demand loads. Okay, you had to promise extreme reliability, and you had to deliver low-cost electricity. The only way they could meet that objective was essentially with dispatchable generation, which, they had in spades. They had fairly primitive controls as far as the grid is concerned. They had LTCs, low tap changers. They had a few voltage regulators and sectionalizers and breakers. And so it's electromechanical switchgear, essentially, which was being used to control this. But, face it, this was working reasonably well, or very well, I'd say. They were able to maintain very low cost. If you look back just a few years, 2004, EIA estimated that by 2030, you'd get maybe 3 to 5% of renewable penetration. That's been blown out of the water completely. So you can see that, that some things are starting to change. So as we started looking at this whole issue of Smart Grid 1.0, I just want to remind everybody that the utilities have been implementing essentially what, amounts to putting a layer of IT and automation over the existing grid assets, for over 20 years now. What's changed now is the price of IT has gone down, the price of communications has gone down, and they're able to do this a little more effectively. And what you start seeing is that, they're being very sophisticated about how they're operating the grid. They design for optimal power flow, they design for N-6 contingencies, and there's the alphabet soup of FDIR, DA, AMI, everything, that you can throw at it. So let's take an example and see how a typical utility would implement what I'd call a very typical smart grid function. So, here's what I'd call a best practice implementation, courtesy of EPRI. This is kind of from one of their pictures. It shows a volt-var optimization system. And you can use this to implement things like conservation voltage reduction, which allows you to squeeze more capacity out of your system. So the way you do this, as I said, is by laying over, IT on top of existing grid assets. We talked about AMI, so AMI is a part of it possibly, or additional sensors are. And so you have all these sensors giving data back. You're computing what the best, action is based on the location, the configuration of the network, and it's a very sophisticated, calculation. But at the end of the day, what you're doing is, once you've gone through this calculation, you're going to tell your capacitor banks to switch in or out. You're going to tell your, LTCs, what switching they do. And so you've put a very expensive $200 million system, okay, and at the end of the day, maybe you're reading the meters every 15 minutes, maybe you're getting data every 15 minutes, but you're still limited to 3 to 4 times a day that you're able to switch your capacitor banks. And so, you can start seeing that there's maybe some disconnect out here in terms of, the ability to sense and the ability to actuate. And then if you look in the future, you start seeing that this is actually going to be changing even more substantially. As we start moving towards RPS mandates, where we're starting to see, 15, 20, 30%, PV and wind penetration, and you start seeing the dynamics of what, solar energy looks like, what you start seeing is that even on this distribution feeder, you start seeing fast, voltage variations, which it's almost impossible for this technology to cure. So what we have here is, utilities are acting very smartly. They're, acting with all the assets that they have. They're putting all the, layers on top of it. But at the end of the day, if you look forward, okay, and you anticipate all the things that are coming down the pipe, you do not have a solution that's going to be able to meet the requirements that are there in the future. So in addition to, the smartness, what we're really, requiring is some level of dynamic controllability that is missing, in action at this point in time. So, can we do this the way we've been targeting? Yeah, absolutely. I mean, there's really nothing that suggests that you cannot take the existing model of operation, business as usual, and add to that the intermittent renewable generation, and the unpredictable loads such as EVs and everything else. And if you now operate the existing T&D network under the same requirements, for reliability and contingency as you currently operate, you're going to have to build an awful amount of new T&D, network to be able to support that. And what you're going to find is that the cost of energy is going to go up, the cost of installation is going to go up. All of those elements are going to go up. And so, again, I mean, if if we can put dynamic controllability, and if you can justify that the overall investment that is required to be able to absorb the new renewable generation and the new load patterns into the system, is much lower, then we have a business case to be able to move forward. So here's an example of what today we cannot do. Most people who are not very familiar with the electricity industry, when we hear of markets, we presume that it works pretty much like markets do. I mean, all of you, pump gasoline into your car, and when you pump gasoline, you can trace back where that gasoline came from, all the way back through the pipelines, all the way through all the dealer networks, and all the way to the refinery plant. And you can, in principle, everybody along that way made a nickel, and that's exactly how markets operate. So when you're delivered a service from somebody who's willing to provide you the service, and you use a pattern of load delivery, okay, you should be able to get market signals from that. Well, it turns out that in the utility or in the electricity sector, you cannot control where power flows on the grid. And so what it ends up with is really put severe constraints on the way we use our system. So, you end up, by the time you put your N-1 or N-2 contingency utilization, you end up with, 40-50% or less utilization of your major asset base. You end up with congestion problems. You end up with great difficulties in mitigating congestion. In a market situation, you want to be able to deliver differentiated products. You cannot deliver differentiated products out here. If I want green electrons, I can't get them. I mean, we did some experiments when I was at Georgia Tech, and we saw that on a typical grid basis, if I wanted to dispatch power from point A to point B, I was only able to get 5% of it actually coupling through. So you don't really have good control, and all the people who run transmission networks know that that's a significant problem. Now, does that mean there are no solutions? No, obviously not. I think we have a lot of companies who've been working in power electronics and have solutions that have been presented commercially, like HVDC systems or back-to-back systems, various kinds of fax devices. And so solutions abound, but why haven't these been adopted in much wider scale? I mean, it's very clear that if you don't have control of the network, you do not have a very good ability to accept variable resources such as renewables. Reliability is down, and cost is up. So one way you can think about this problem, and this is part of what we are doing with ARPA-E, is the whole concept of power outing. Is it possible to be able to put a thin overlay on existing networks and to be able to route power from point A to point B and to do it at a low cost? And if you could do that, then all of a sudden you'd be freeing up grid capacity, so you wouldn't have to build as much of T&D to be able to implement. You wouldn't have to build as much to be able to absorb energy. Hey, and if I could deliver energy to somebody who wants green electrons or who's a little flexible in terms of what they're able to absorb, you now have a market that begins to operate. The transmission industry starts getting signals that says that, hey, have a congested corridor out here, have spare capacity. Can somebody make the investment in that and be able to route power that way and be able to bring down the cost of energy? So again, overall what we see is that there's an opportunity out here to begin to bring dynamic control to the grid, whether it's in terms of voltage or in terms of current, in terms of power flow. And the way to do it is not a brute force approach, but to do it through incremental deployment, to do it with a way that is synergistic with the existing grid so that costs go down, and to do it with something we've been calling fail normal. So when the less reliable power converter fails, you still have the original grid is there, and so that overall system reliability is not impaired in any way. So, if we start looking at all this, I mean, we've kind of seen and shown that you can then start thinking of the existing T&D infrastructure being used, to absorb more renewable energy, to use spare capacity on the grid to create a whole new category of loads we are calling flexible loads, which can be which can use the smarts in the system to do the coordination. And so if you can now do this, if you can control voltage and power dynamically, if you can match the intermittent generation to flexible loads, if you have fast response, if you're not burdened by a huge IT infrastructure, if you can maximize the use of T&D assets, and you can get the reliability, you might be able to get new market functions, you might be able to get differentiated power delivery, and I think that's the real objective. So when I look at what's beyond smart meters, don't get me wrong, smart meters are great. I wish we had a much stronger ROI for them as we've rolled them out. But really, I think by tying it to, how can we get more out of the asset base? As a CEO, you worry about your assets not being utilized effectively. And if I'm on the grid, I'm looking at this and saying, man, I have some lines that are running 30% loaded, how can I get more through that? And how can I turn that into revenue? So I think I'm painting a slightly different picture than my friends here have, but hopefully this is all stuff that can stimulate discussion. Thank you very much.
Thanks, Deepak. So I'd like to... So, with the introductory words from each of the panelists, I'd like to would like to open up the Q&A. So, people in the audience are welcome to make their way up to the microphones. While you're making your way up, and one of the things I'd like to point out by way of contrast is, we had a panel discussion this morning, and in that panel discussion, we had the chairman of Microsoft in discussions with the Secretary of Energy. And one of the interesting things that I hope all of you notice is when we were talking about what innovation was necessary on the grid, the chairman of Microsoft basically suggested nuclear reactors. And here, when we basically have 4 experts who actually work on the electricity grid, notice that all 4 of them really talked about information technology being critical to the evolution of the smarter grid. That all 4 of them basically talked about new ways of using that information to be able to actuate and make the grid more intelligent. And at least 2 of them talked about the idea of being able to make an internet, right, a power-routed grid. So it's interesting to see, maybe I think an important part of the discussion, hopefully, that we'll have today, is what is the role of IT? What can we communicate maybe to companies like Google and Microsoft that don't really see where the computational challenges, where the IT challenges are, that you guys have addressed, and maybe how to engage with that broader community. So maybe I'll just point that out as an observation and maybe take questions.
Hi, Zach Coleman with Smart Grid Today, and my question is related to control system cybersecurity. There's a lot of talk that control system and IT don't always see eye to eye when you're implementing some of these cybersecurity programs. Can you discuss how standards have evolved around this issue, and also how you're implementing them at your own centers?
So Arshad, you want to start with that?
All of you have heard about cybersecurity, and the way we look at it, cybersecurity is not that you need a magic box technology solution that will make all control systems secure. I think it's a matter of people, it's a matter of processes, but it's also a very big part on cybersecurity discussion that doesn't get into that discussion is the resiliency of the grid. Because one way, when you can never spend enough money to ensure that you're 100% cyber secure, we will not be affordable anymore. However, detecting intrusion and then the ability for the grid to gracefully respond so that the event can be contained, I think that would be a big part of making sure that we are not vulnerable to a cybersecurity event causing a widespread impact.
Paul?
I don't, I think to part of the question that you're asking, I don't see so much a difference between the IT and the control systems point of view. I think over the last 5 years, I think people have come to understand and appreciate which each community sort of brings to the table. That is, you can't just simply apply some techniques in IT to some control systems. You need to understand kind of the context in which the control system operates, and vice versa. That there are a lot of lessons that the control systems folks have started to learn from their IT colleagues in the dialogue that's been happening, as I said, for some years now, as manifest in, for example, the NIST activity with the Cybersecurity Working Group under the SGIP, that Arshad touched on, that NISTR that came out around how to think about the convergence of IT and sort of this operational technology and control systems in particular has been very good work and is really helping a lot. I think fundamentally where people are at is not so much the greenfield opportunities, that is when you go to replace a system wholesale, and then how do you start to address that, because from there you can start from building it in from day one, which is clearly one of the lessons that was learned out of the internet, is you want to do that from day one, not think about it 10 years on. However, we have so much infrastructure already out there, and as was touched on, not all this infrastructure is 50 or 60 years old with respect to control systems because of the investments that have been made over the last 20, 25 years. And so how do we think about a graceful migration of an integration of those technologies into a secure schema that addresses both the need to secure the systems, but at the same time be cost effective, because at the end of the day, all this ends up in the consumer's rates. And so we also have to be aware of the impact, particularly in these challenging economic times, on what it means for the end consumer.
Okay, let's take a question from the right side.
Mladen Kizunovic with Texas A&M. I have to be careful with this question. I have two people on the panel that are funding me, and one knows that, and the other one may not even know it. This is the question I have. We have all of these technologies that are really great opportunity, and the question is, how do we match the technologies to the business processes and business models that exist in industry? Because it's not an easy problem at all to solve. I'll take an example or two that you used as panelists. For example, the issue of data that was mentioned by EPRI. We all are aware of the benefits of data and have been for a long time since the data was available. But there is a sense of ownership of data in the business today that is associated with the infrastructure that collects data. If it's a SCADA data, we know who the owners are. If it's relays, we know who the owners are. This is just a small example. So how do we change these business processes to actually adopt some of the things, take advantage of them across, say, utility industry and then across the stakeholder community? And I personally see that more of an issue than the technology. And so I would appreciate if you could comment on that, please.
Thank you. I can start. I think, again, as you approach the business case, let me just give you one example of a type of development. Valuing flexibility is something that we probably need to do more of, but to actually say, let's put a value, a dollar value, if you will, on somebody, a customer saying, I'm willing to be flexible. And I think if you try to take that with a traditional model that says, okay, I'm going to acquire a customer, I'm going to be responsible for serving that customer's load, making sure it gets served reliably, et cetera, et cetera, et cetera, and I'm going to try to incent it to provide flexibility, the whole thing will collapse. You can't do it. However, if somebody says, I'm going to go to a customer, I'm going to tell them for one particular device they have, allow me to turn it on and off remotely. Just that device. I don't care about where you get your power, who pays your bill or whatever. I just want, I'll give you $25 to let me hook that onto your system and you won't even know I'm here. We actually saw this occur in New Jersey, where they did this with 100,000 residential customers. They offer that to us as synchronized reserve. They go through a wireless grid to essentially allow those individual devices to communicate. Very simple device, on or off status, et cetera, et cetera, et cetera. It ends up getting paid in our market to provide synchronized reserve, 10-minute response. It's not a very fancy system. The business model actually worked, though. But they had to completely change the way they thought about what a customer is to them. A customer is to them somebody who happened, they visited one time, who happened to let them put a device on their system, and then they walked away. So that type of thing is actually trying to identify the value. In other words, what's the dollar value to the grid? In our case, thankfully for those folks, we actually put out a price for the value of synchronized reserve every hour. But I think it's that type of putting together the technology with what's the value where I believe the answer lies. It's not in saying I've got to be full service to customers, and that's the only way to deal with it, because that's been in this industry, I think, too long. I don't know. I'm hoping I'm answering part of your question, but I think it's look at how much it costs you to do something and what can you get for it, as with any business. But it's trying to figure out a way to do it in this kind of world.
Just to add to what just Andy said, I think one of the things we're seeing smart grid is doing, it is breaking down organizational silos, and each silo has their own data. Right. So if you look at a utility system, you have an organization that owns the SCADA data, you got a different organization that owns the smart metering data, you got another organization that owns the DMS, distribution operations data. And when you try to optimize the system operation, you have to seamlessly share the data in a secure way. And we are actually seeing that happening now, but you are very much correct that that organizational data silo has been one of the impediments in fully using the data. It's nothing new, though. Any organization that gone through a enterprise resource planning SAP type system, it's not the system or the technology that's the challenge. The challenge is how to get the right data to the right owner so you can run the business analytics to make use of the data. Same thing for smart grid.
Yeah, I would just, maybe also to your point, I think it's important to recognize where we are in this evolution. I would say 10 years ago, when efforts like EPRI's IntelliGrid and the Gridwise Architecture Council were started with the idea of how do we start to link business value to technology choices, because that's really what those efforts were about. And sometimes there's phrases that certainly in my last role we used business architecture linked with technology architecture as a phrase. But this idea of starting with business need driving to technology choices, and I think the efforts over the last 5 years in particular around, and a lot of adoption here in the United States and starting worldwide around systems engineering approaches, starting with this use cases and business value driving then the choices and decision making. But the other thing to come full circle is we're now at the stage at which a number of the deployments have happened such that now you can start to get the data. You can also, people are starting to realize the real economic value out of these systems, some of which they kind of anticipated at the outset, but some they didn't anticipate, and they're realizing that there was other value that was sort of built into these systems that they're actually able to monetize today through reduced operating expenses or increased value or customer satisfaction. And so we're starting to see results of that, both out of the demonstration projects, out of the investment projects. There was a report out just a week ago from the Gridwise Alliance articulating a whole set of economic values out of smart grid investments that have been made to start to highlight this. EPRI's own work last year on the value of the smart grid pulled from some of those same. So I think we're starting to see that life cycle be played out and can build on it. We're not all the way there yet, but I think we've got some good foundational pieces laid.
Rajeev, just...
Okay.
Yeah, go ahead. Just a quick comment. I think maybe you raised the issue, Arshad, that the data is resident in silos, and what's the cost of getting the data across the silos to somebody else who can use it in a meaningful manner, and how do you parse that data down, and what's the cost of that, and how do you extract the value from it in the ROI case? I think these are probably things that haven't been fully understood and vetted. And then, is this just the IOUs who can afford large IT organizations who have this? What about the 2,700 co-ops and munis and everybody else? I mean, how do they share in the benefits that come from this? So I'm not sure that all the answers are there in a very simplified approach which is completely, IT intensive. But, and I think all of these need to be addressed at the same time.
Thank you.
We'll take a question over there.
Dave Watson, Lawrence Berkeley National Lab. Many would agree that some form of dynamic pricing is required in order for these business models to work to somehow more closely couple the supply and demand. So I'd like if some of you could imagine if you were king for a day or could just write the rules yourself, what form of dynamic pricing would you recommend?
I guess I'm the price guy. So probably something that would actually be workable would be something that would be similar to something called a critical peak price rate, where there's some ability to guarantee a price for a period of time, but when the system is experiencing very high stress or very high price, that's when you would essentially want to incent or reward, depending on how you look at it, flexibility. So it'd be something that provides a fair amount of certainty most times, but has a fairly high incentive for the right type of response during either high price times or in fact very low price times, which is coming more and more often. But I think you couple that with automation type technology. I think another emerging type of thinking out there is if innovators can figure out ways to use automation to make essentially the customer not even realize they're providing services back to either power grid operators like us or to utilities through automation, so it's sort of painless to the user, if you will. If that coupled with this type of rate where it provides some certainty while still doing some reward, seems to be the most practical way to go, because let's face it, you're not going to have the volatility of real-time pricing or anything close to that. So that would probably be my, if you were king for a day kind of observation.
I would add that I think there probably needs to be a little broader discussion about the temporal dimensions of pricing related to what it is you're trying to incent and encourage. And real-time spot market prices are great for sending signals about certain aspects of the grid that you want to have accomplished, but they aren't necessarily great for long-term investments. And so if the public policy is to incent long-term investment, whether it's by the end consumer, whether it's industrial, commercial, residential, spot market price isn't necessarily the thing that's going to get that done. And frankly, that's where a lot of people looking at business models trying to reconcile these two. They each have a place, so it's not one versus the other, but I think there should be a broader discussion about this than I think we've had to date. I think the other thing, while things like prices like LMP prices reflect some information about transmission system constraints, when we start to talk about the integration of end-use loads or resources into the system, prices need to reflect what's going on in the distribution system. And today the LMP price is sort of ignorant of what's happening at distribution. And so if we're going to try and have a mechanism to, say, leverage or be able to monetize the value of what Deepak was talking about, you're not going to do it through just an LMP price. And so there's an area there, I think, to have further discussion about how to reflect that.
Yeah. I agree. I think, when I think of flexible loads that can kind of most benefit the system, electric vehicles come to mind. They need to charge for 4 or 5 hours, or stationary 21 hours. So, when they get their electrons is probably, can be determined by the utility. But it's not just, what the price is that's being conveyed. It's where's the congestion. Some of the analysis we've done shows that if you get 20% EV penetration in a community, transformer life can go from 35 years to 3.5 years.
Right.
Okay, and that's a pretty significant, and the RTO has no visibility to any of that. And so the pricing process really needs to integrate all the way down, and kind of look at where is the congestive block, and what is the value of relieving that or accessing that. And which is why I was saying that there's coordination that needs to be done. It's not clear that the existing business model of setting prices from God is really the way that's going to work overall. So.
Here, question on this side.
Jaime Ramos, University of Texas, Pan American. We have constructed a microgrid. Our resources are 5 kilowatt photovoltaic, 200 amperes 48 volts batteries. We can measure solar resource with radiometers. So then my question is, imagine your workspace is a local area network, or at most a business area network. So how small, not how large, can a smart grid be? We want to construct a smart grid with a handful of elements, a handful of smart meters. So we are looking for solutions which obviously will not be like utilities solutions because of our scale and also because our operators are going to be the students who will be operating the system and who will also be creating the applications. Of course, we have idea of classical electrical engineering applications.
I'm sorry, I'm trying to make sure I understand the question. Are you asking a question about how granular?
How small can the smart grid be? I am aware of the IEEE interoperability smart grid guideline, which was published in 2011. So, do you know of any other standards that I can look at that? And then my question would be, do you think what I intend to construct will be a smart grid? Thank you.
So what I'm understanding is like how small can a test bed be in order to still be considered a smart grid?
Yes.
I mean, I think for this panel, I think we're not really looking at sort of an academic study of smart grids, but really trying to understand, looking at scaling for large-scale systems, large-scale deployment. So it may be something that was best taken offline to kind of think about, what do we do on a test bed scale? Right. So maybe with that we can.
Rick Bush, Transmission and Distribution World. Hi, guys. Yeah, I wanted to make a comment. We heard this morning that there was no silver bullet, or maybe there is no killer app, but I would posit that there is a killer set of apps, and I'm seeing a lot of those killer apps downstairs. So I'm envisioning a day where particularly regional distribution will be connecting one entity connected to the grid to another without necessarily being able to define whether that entity is a customer, a generator, a storer, a restorer. So I think we're coming up to a new world, and it seems like we need to have a new understanding of what distribution might look like before we start to build out distribution.
It's me. I think, Rick, you will be surprised to see not just killer app downstairs, but this whole concept of knowledge engineering is going to proliferate in our industry. I'll give you one example of a killer app. It's actually happening right now. You can get mobile platform now for $200, $300. That mobile platform has a camera. That mobile platform has a GPS. So think about your field crews who are driving by. They can actually point that mobile platform to a pole. And the GPS. You can directly go to your GIS system and correct all the wrong information that we have on many of our GIS systems. So I think mobility integrated with camera tools are becoming very, very cheap. With GPS, I think you will see apps happening in the distribution world that we haven't even seen today. So and this is all part of, it's not the next generation algae or the next generation biofuels. It's knowledge engineering using the IT tools that now exist in our domain to make us more reliable.
So we'll see these killer apps on both sides of the meter.
Right. So I think, just building on that point, you've got two things happening simultaneously from the utility side of the meter in distribution. One is what Deepak was touching on, and what I mentioned with respect to how the physical operation of the electric system at distribution is going to evolve to incorporate millions of distributed energy resource for any particular service area, potentially. And certainly looks to be the case in places like California, to name one area, by the end of the decade. But the other is you've got the convergence of voice, video, data, and mobility coming to the operations side of the house at distribution, and these two are sort of coming together as well at the same time. So you've got a lot of change happening that isn't probably perceived by people on the outside, that is really going on fundamentally in terms of rethinking how both you operate, both from a field force standpoint and business operation, as well as how the physical nature of the network is going to need to evolve. Not to mention, right, what's happening in terms of on the other side of the meter, in terms of the innovation that's going on there, and some very innovative technologies that are that we were talking about here about wouldn't it be nice if it existed, and in many cases those technologies do exist in terms of early stage or in some of the growth companies that have technology. The question is, how do we start to put the puzzle pieces together in a way that provides the same level of reliability and the same sort of cost-effective manner that we've been producing and supplying electricity for over 100 years.
So I just want to so we've got a few minutes left, so maybe I want to make sure we get to the 3 questions that we have on the side. So
my name is John Bobrovich. I'm with the Wisconsin Energy Research Consortium. You've talked about a number of factors that are going to influence the smart grid going forward. One of those is distributed generation. I'd like to ask you what your opinion is about the microgrid as potentially a self-balancing source. What kind of penetration into the system your models are showing for the microgrid going forward? And I'm curious if that's in alignment with the kind of market projections that are out there right now for $3 to $5 to $10 billion a year microgrid industry in the country.
So it might be useful to define microgrid before moving on to answering one of the question about penetration.
I can do that. I mean, the way we work quite a bit with microgrids, and we at least I would define a microgrid as a subset where you have at least one generation source and a connection of loads, possibly with a connection to the grid. Typically multiple generation sources, maybe some storage, and you can do some local optimization. There's some challenges with the microgrid in particular. Is it a power quality microgrid? Is it a reliability microgrid? And what's the ROI? And the ROI has never been very clear, except for some of the work we've done with the Army, where it makes a lot of sense. But to kind of look forward, I would suggest something that is really very interesting. I mean, I think Secretary Chu said it today. I mean, the big changes that have happened is, the price of solar has dropped and is dropping more and more and more. Okay, and natural gas prices have dropped dramatically. Right. So is it possible to think of a future where you have gas supplies at every house maybe, and you can think of marrying that to PV and some lower cost energy storage that Rajeev or other friends at ARPA-E can generate, and you now have each house becomes a microgrid where the grid is maybe not required. Why, if something works in Africa very well, why can't it work out here? Okay, so I mean, I can think in the future sometime you may actually, and especially if the utilities don't respond the way customers want, or those prices go down, you may actually see the microgrid take off and become a way of life. But it's not there today.
So maybe I can ask, maybe Paul, you mentioned this idea of prosumer, but how do you basically contrast the prosumer concept with the microgrid concept?
Well, that's a good question. In my mind, the microgrid is, as Deepak said, I view it in that context as a relatively narrow market. However, I do see the other view, which is the virtual power plant. That is how you take distributed resources and integrate them into the larger sort of energy ecosystem, whether it's at the distribution level or into the broader markets on some level, even maybe at a community level. I see much more from an economic standpoint, more rationale to get to the return on investment, to be able to monetize that beyond just a small community, setting aside something like, say, the Army or Department of Defense, or say a university campus or the like, some of the classic microgrids that people have talked about. Certainly those exist, but I think that to the extent that we're going to see, and I do believe we're going to see, as Secretary Chu said, significant penetration of distributed solar and other distributed resources, why wouldn't you want to monetize that to the full extent, particularly in those periods in which you're overproducing for what your own need? And so as a result, I think that you're going to want to participate in markets, and therefore I think it goes more to the virtual power plant model that people talk about, as opposed to a closed system microgrid.
Okay, so we have about 2 minutes left before we go to closing comments, so maybe we'll take the last 2 questions very quickly.
Yes, I'm Joe Byers, head of a company called Invenergy. It's a collection of companies, several of which are energy related. Paul, since you were a board member of one of my companies, I won't direct a question to you, but question is more directed to EPRI. In my former job in HP, one of the many things I did was responsible for standards, and HP was involved in 300 standards implemented in 100 different standards bodies. And what I found out in that process was most of these standards issues were business issues, not technical issues. You mentioned the standards activity in this space has a heavy technical content. I'm just curious your thoughts on that, and if you could elaborate, what are some of the key technical issues in your standards processes?
No, I think if you look at the way standards has evolved in the electricity industry, if you look at some of the key standards, at the end of the day, the primary focus of most of the standards is defining the data object models. It's really naming structures. It's the object models. And I see, at least from a distance, I know, Paul, you are much more engaged, the technical issues are dominating now. The business issues are there in the fringes. But right now the technical issues is how do you communicate effectively using the same language? And language has several status. You have all the way from the object to the communication level. So at this point of time, I don't see the technical issue, the business issues preventing us from moving forward. It's just it will take time. We just have to get real that when you're trying to get an end-to-end integration standard all the way from a thermostat to an EMS system that PJM will manage, it ain't going to happen in a year. It will not happen in a couple of years. It will take time.
Do you see EPRI taking a leadership role in that process?
Well, our role is to provide the technical content that could help in developing the standards like many other organizations. At the end of the day, the Smart Grid Interoperability Panel led consortium with the standard-making bodies like IEEE, IEC. They have to take the lead. But somebody will have to do the technical work, and EPRI will do some of it like others are doing.
So let me just take the last question from Nari.
I'm Nari Hingorani, consultant. Thank you, Rajeev, for not telling me to sit down. Time is up.
Okay.
Anyway, the question is the right one. Future grid beyond smart meter, assuming there's a question. No one has said how are we going to modernize our transmission system, without which we would not be able to harness wind resources or take advantage of diversity of resources and time difference in time and so on, which is the reason for having transmission grid.
So most of our discussion today has really been about thinking about distribution. So maybe Andy, I can turn this over to you since you are actually a transmission operator. How do you see the change in generation mix, the smart grid, demand response, all the distributed generation that we've talked about? How do you see that impacting the transmission system?
Yeah, I think as we look at the penetration of not only I'll call it variable resources, but also the lack of capability on the supply side to provide response service. What we're seeing on the power grid again is there are times when we have situations where we really hadn't had it before, which you have locational, for instance, areas where you have extreme negative prices, which essentially are effectively a minimum generation emergency type situation. So you see those popping up more locationally than you've seen in the past. And what effectively on the transmission operations side, it's bringing up some unique challenges as far as dealing in light load situations that we hadn't seen before. We're actually evolving our planning process to look at light load scenarios almost as regularly as we would look at some of the heavy load scenarios. So as we look to plan the system, we've had probably through just the period of the fall because of some of the loading patterns, some of the differences in the way we've seen the grid and light load. We actually had over voltage situations 27 days out of 30 in October. So the type of control we need and the type of scenarios where we're doing line switching and different operating scenarios. Need for better control system. That's why you saw me discuss the very fancy dispatch device that we have, algorithms that we have that actually give us a lot more situational awareness of what we're seeing on the grid. So I think the reaction on the transmission side is we're able to try to stay ahead of it by seeing much more visibility and accuracy into what the state of the grid is. And so far we've been able to manage it at a relatively low cost. I think as we go forward in time, that's really the answer is better situation awareness. Obviously the phaser, advent of the phaser measurement units, et cetera. I think we'll be able to deal with on the transmission side using that, and obviously price signals then incent the flexibility like I was talking about. So I think probably that's what I provide as an answer, that while it'll be different, I don't think it's unmanageable.
So how about on the infrastructure side, either Arshad or Deepak? Yeah.
I just want to add to this. I think what you saw today, if you can come up with a cost-effective, high-voltage, low-loss switching device that will allow you to make flexible AC transmission systems, because the system is going to get a lot more complex 20 years from now than it is right now. Power flows are already changing from all over the place, and it's changing on a almost minute-by-minute basis. So flexible operation of transmission enabled by a power electronics building block that has the low loss, low cost, the thing that you saw this morning, I think that would be a game changer on the transmission side.
So maybe I could ask, just by way of closure, so if that happened, if this came to pass and that technology vision occurred, how would that affect consumers? Like, how would a sophisticated consumer know that the grid basically had this kind of, the transmission grid had this kind of flexibility built into it?
I think you would see, and obviously these don't happen very often, but I don't think you'd see, the widespread outages, or if you did have some regional outage, it would be much more contained. One of the things that happens with these large scale outages is a result of it not having enough situational awareness. And maybe one thing I can agree on with Gates, his comments this morning, is that the human factor in the decision making is being outpaced by the situations that are happening and can occur in some of these extreme events on the transmission system. One of the things that is going along the lines of what we're talking about here is that the temporal dimension is collapsing to very short time periods as we talk. The system has for a long time operated on a 4-second basis, and with the wide-scale adoption of synchrophaser technology, which measures today at a 30th of a second and quite likely going to a 60th. In Europe, they're talking about 120th of a second. That is measuring what's going on in the system on that basis. We're going to be able to move from the equivalent of being able to look at something in terms of resolution of an X-ray to an MRI in terms of the health and strength of the grid. Moving to that short time dimension, though, means that all your systems control systems and like need to start reducing in time too, to the point at which humans can no longer process what's going on to be able to react, and therefore, as this panel's been talking about, the role of analytics and these more sophisticated control systems and the tools that allow you then to take action are coming together. And so it's going to be quite different, but the result from a consumer standpoint is, presumably, much less of these large-scale, blackouts.
Reliability, affordability, and environmental responsibility. As a consumer, I want the lights to be on. Yeah. And if the fax device exists 20 years from now, the lights will still be on, even though we have a lot more complication in the system, a lot more variable generation like wind.
And I suggest it's better to us in the industry that this consumer doesn't even see the difference.
Yeah. The lights are still on.
Their cost didn't go up, and their lights didn't go off, so therefore they don't care if the fax device is there. That's the best answer.
I'm going to say something slightly controversial and different. We've been mollycoddled and spoiled because, we've been given, great energy, very reliable. I come from India. 6 hours a day with no electricity. Now you start valuing what electricity means. So, when I take my cell phone out, half the time I think, can you hear me? Can you hear me? Nobody ever asked that question when you turn on the light. So I think we're providing a resource at a very low cost point and have made people forget the value. So I really think that there needs to be a gradation of value. If somebody wants on-demand, ultra-reliable, they need to pay more for it. If they're more flexible, they should be able to pay less for it. So unless you're able to create that level of, diversification in the consumer base, he's not going to care, because as a consumer, what do I want? I want the lowest cost, and I want the lights to be on. Okay, and yes, I'll give lip service to the fact that I want to be green, but if my costs go up, I'm going to push back like hell, and say, what the hell are you doing out here? So I really think that, we want our cake and to eat it too.
And we do.
Absolutely. And so I think, the fact is that,
we're proud of it.
Absolutely.
We want the
let's
same
not say that we want green, okay? But if you do want green, then that's fine. I mean, I like green more than anybody else, but, then we need to be able to accept the fact that, you're going to see a gradation in service.
But that's a great challenge for technologists. Keep it green, keep it affordable, and still keep it reliable.
And keep the cost low.
Absolutely. For scientists, for technologists, that's the biggest challenge that you have. So we don't
now
want
that
to
we've solved that problem, I think we're all done.
So now that we're all warmed up, I think I'd like to thank all the panel members participating. Thank you all.